Hello and welcome to this Chemistry World webinar, introducing Azure Quantum Elements, accelerating scientific discovery. I'm Natalie Starkey, Chemistry World science media producer, and I'm here with you for the next hour. Now today, we'll be hearing from Dr. Nathan Baker from Microsoft. So Nathan, would you like to turn on your camera so the audience can see you? There we go. Hi Nathan, good to see you. So Nathan's also here to answer any questions you have about today's topic, and I'll explain in just a moment how you can contact him. So Dr. Nathan Baker is the Head of Partnerships for Chemistry and Materials, Azure Quantum at Microsoft. Previously, he was a Laboratory Fellow in the Physical and Computational Sciences Directorate at Pacific Northwest National Laboratory in the US, as well as an Associate Professor of Biochemistry and Molecular Biophysics at Washington University in St. Louis, also in the US. Dr. Baker is a member of the Washington State Academy of Sciences, a Fellow of the American Association for the Advancement of Science, and a former Alfred P. Sloan Research Fellow. In his presentation today, Dr. Baker is going to introduce Azure Quantum Elements, a comprehensive system that empowers researchers to make advances in chemistry and materials science with unprecedented scale, speed, and accuracy. With it, organizations can accelerate scientific discovery and bring innovative products to market more quickly and responsibly. He'll explore the recent breakthroughs in molecular simulation, which provide exciting new possibilities for computational chemists and materials scientists. He'll also discuss the latest advances in high-performance computing and AI, and describe how to start using Azure Quantum Elements today. Now, before I hand over to Nathan to begin his presentation, I want to remind you that you're able to ask him questions that I'll be able to put to him towards the end of the webinar. As a quick explainer, on the GoToWebinar platform that we're using, there's usually a panel down one side of the screen, although this might be different depending on which platform you're using, especially if you've joined us via a tablet or phone. Now, somewhere on that panel, there's a questions box, and you can feel free to pop your questions in there at any time. Now, during Nathan's presentations, I'll be back with some poll questions that we'll be asking the audience. But without further ado, I'm going to hand over to Nathan to begin his presentation now, and I'm excited to hear what he has to say.
Great. Well, thank you very much, Natalie, for the introduction, and thank you to RSC for supporting this webinar, and thank you to all the attendees who've called in today. I appreciate you spending the time with us. I'm very excited to tell you about Azure Quantum Elements today. As Natalie mentioned, this is a platform that's been designed to accelerate scientific discovery with a specific emphasis on chemistry and material science and accelerating the atomistic simulations that underpin those. So I'm going to jump in with probably a slide that's not needed for this audience, but I'll start anyway with why do we care about chemistry and material science? So anyone who reads an issue of Chemistry World each week sees lots of great examples about why chemistry and material science is important to the world. Microsoft believes that chemistry and material science are the keys to solving some of the most important problems facing the planet today. So whether that's food scarcity, whether it's pollution, whether it's issues surrounding climate change, all of those problems most likely have solutions that depend on innovation in chemistry and material science. So that innovation and accelerating the pace of innovation is really an existential requirement. We have a wonderful quote from our CEO saying we need to compress 250 years of chemistry into the next 25 in order to be able to meet these challenges, and we firmly believe that. As you'll hear throughout this talk, we've built the Azure Quantum Elements platform to help solve those problems now, but also to serve as an on-ramp to future quantum computing. And that's the other reason why we're focused on chemistry and material science. When we think about the problems that are going to have the maximum benefit from quantum computing in the future, those problems have quantum mechanics at their basis. And in particular, they are the chemistry and material science problems that rely on computational tools. So with that, we'll start with our first poll of the seminar. And Natalie, I'll turn it over to you.
Brilliant. Okay, so we're just going to share a poll on the screen that the audience are able to interact with. So we'll just give that a moment. So the question is, does your company utilize digital modeling, computational chemistry, or simulations for materials or product development? So you have yes, no, or not applicable. So you can just click on the screen and let us know your answers to that question. But also, please feel free to put any comments in the questions box. You can also use that to send us any comments. We love to hear from the audience, and we love to, if not applicable, please tell us why. But yeah, if you want to give some more detail, that would be great. We're getting loads of responses in already.
Oh, fantastic.
Yeah, so we've got okay, so we're going to say over 50% of the audience are just gone under 50% are a yes to this question. So that's probably good for you to hear.
It is, and I'll keep talking then.
Yeah, brilliant. So we've had quite a bit of the audience voting. I'll just give people a couple more moments to get their responses in. There we go. Okay, so I don't think we need to share the results necessarily. It's a fairly simple poll. So we've got 51% of the audience are yes to that question, 19% no, and 30% it was not applicable. So I'll hand back to you to your presentation.
Okay, thank you very much. Great. So I mentioned that we're building this platform to accelerate the pace of innovation in chemistry and material science. And we believe that acceleration is going to happen through a paradigm shift in research and development. Now, this is a long-standing sort of promise in the field about computational chemistry. One of the goals for computational tools in performing that acceleration is to really help experimental studies focus on the most promising leads. So rather than starting with, I guess, an Edisonian approach, if you will, of trying lots of possibilities and then using computation to find out why those worked, why some worked, and why others did not, our goal is to make sure we lead with computation. Computation suggests the right experiments to do. It helps scientists focus on the most promising leads first and really serves as a co-equal partner in that process. But as we'll talk about, there's challenges that have held back that promise in the past, and those are the challenges we've designed the product to address. But before we do that, let's do another quick poll about applications and industries that the audience is interested in seeing.
Yeah, these are quick fire polls today. I like this. Okay, so we'll just get that one up on screen. Okay, so the question is, which industry are you interested in seeing example applications for? Now we've got five options down here: manufacturing, energy and environment, healthcare and life sciences, consumer goods, and academia. Now, if you don't fall into any of those categories, please let us know in the questions box. You can put in your, the industry that you're interested in or whatever it might be. Or if you want to give us some more detail about any of those industries, that would be fantastic. I can see that questions box, so I'll be able to see anything that goes in there. So we're getting lots of responses. It's a really good spread, apart from consumer goods, where we've only got 2% of the audience so far in the consumer goods category. So there's a pretty even spread between the others, with energy and environment coming out quite high at the moment, although academia's just caught up. So
feels like we're watching a sports game.
I know, it's really fun. I like doing this. I know. I feel like I should go into sports commentary. Right, okay, I'll give you a couple more moments. And again, do pop in the chat if none of those options apply to you. We love hearing from people and who are watching. Okay, so let's share those results so that we can see those results. So there we go. There's a pretty even spread. But yeah, we've got academia, healthcare and life sciences, and energy environment being the top three. So again, I'll hand back to you to continue your presentation.
Okay, thank you. No, that's great, and I think hopefully for all of those, including the ones not listed in the poll, you'll see applications of elements in each of those domains, in each of those problem spaces. So as I mentioned, we built Azure Quantum Elements first and foremost to accelerate scientific discovery and to help make computational chemistry and material science a co-equal partner in the discovery process to really drive the pace of innovation. But there are challenges that need to be addressed in terms of realizing this vision. And so we've broken the challenges for the platform down into two areas. The first, at the top, you see three technical challenges. The scale of simulations is often limited by the computing resources that are available to a scientist. Speed is always limited. I've never met a computational scientist who said, oh, I'm really happy my simulation was that long. There's always a need for a longer simulation, and we're focused on delivering ways to accelerate that through artificial intelligence. And then accuracy. As we'll talk about at the end of the talk, one of the promises of quantum computing in computational chemistry is to help eliminate some of the approximations that affect accuracy. So those are our three technical challenges: scale, speed, and accuracy that Elements is designed to address. But first I want to talk about the other challenge, and that's productivity. Computational chemistry tools are hard to use. The environments that support computational chemistry tools are often very challenging to set up and to maintain. And those are some of the challenges that we're addressing in this productivity area. So I'll start with the first, and that is addressing some of the complexity surrounding the use of computational tools in chemistry and material science, as well as just getting useful information in chemistry and material science. As you know, Microsoft is heavily invested in artificial intelligence, and in particular on the development of co-pilots to help anyone, any user, address problems in their domain. We've been focused on co-pilots in Azure Quantum to help scientists get useful information and set up simulations related to chemistry and material science. So if you go to quantum.microsoft.com, you'll see an interface very much like the one on this page here. It should look familiar to anyone who's used Bing Chat or Bing AI, but this interface is focused specifically on chemistry and material science. It uses the power of large language models through Azure OpenAI services to perform inference across multiple data sets, but it constrains its answer to things that it can reference from those data sets. So you'll find information from open source literature, so licensed under, say, Creative Commons, so it's usable through this interface. You'll also find information from tutorials, from software manuals, and we put that all together to make an easy to use, natural language driven environment for asking questions and getting answers about problems in chemistry and material science. So that's one of the ways we're removing barriers in this space. The other way, and we'll have a demo on this in a second, is through the interface of Azure Quantum Elements itself. Anyone who has used computational chemistry codes know that these are very complex systems with many, many different configuration options. And often remembering all that syntax can be very difficult. So we built a copilot into the interface of Azure Quantum Elements. And the goal of that copilot is to help generate code. The code is not run for you. This isn't intended to be a black box, but it's intended as a starting point. Maybe saves you time from going through Stack Overflow or trying to look for answers in a particular software package's user manual. The copilot is also designed to make it very, very easy to use workflow tools. Workflow tools are essential in complex computational chemistry and material science tasks, and that's built in as part of what the copilot gives you in terms of code starting points. So the next few slides, we'll see this copilot in action. So I want to start with the primary interface to Azure Quantum Elements. This is actually a web portal front end, so it is your view into the Azure Quantum Elements cluster. And the demo I'm going to show today is going to focus on using Copilot with Quantum Espresso to set up some calculations to get at the properties of different materials. So you go to the web portal, you click on the Quantum Espresso tile, and that prompts you with an interactive session. Basically, it says, how do you want to configure the nodes that you'll be using to run the platform today? So in this case, we pick an AMD series node in Azure. We set up a duration of an hour because we're just going to run this calculation and use it for a demo, and then we launch it. We log into that interactive session after the node is queued up and made available, and we connect over into a Jupyter Lab environment. Jupyter Lab is a core component of the Azure Quantum Elements platform. It provides shell access for those who want to get their hands dirty in the command line, but it also provides a critical Jupyter Notebook interface, which, as most computational scientists are familiar with, is essential for reusable code, for sort of self-documenting simulation and exploration. Now, the first view here in this Jupyter Notebook uses something called a cell magic. Those of you familiar with Jupyter will recognize it. It's the %% command. And the first command we show here is %% chat. That's a way to interact with the Jupyter Notebook in a manner very, very similar to how you would interact with the quantum.microsoft.com Copilot front end. It's for answering questions about different materials, in this case, answering questions about indium arsenide. But a more exciting part of this, perhaps, is using another cell magic %% code. And with this cell magic, we can now start prompting the Copilot within the Jupyter Notebook to help us get started. And as many people know, sometimes the hardest part for a computational calculation is figuring out the starting structure. So here we've asked the Copilot to use ASE, the science environment, to go in and build out a structure of indium arsenide and show us a visualization so we can see if it makes sense before we proceed with our calculations. For the example, we use another cell magic, and now we're going to ask, can you help me calculate the band structure of the material? Copilot is grounded in information about the platform, so it knows which codes are available. It's also grounded in knowing that AIDA, as a workflow manager, is the way that we handle most complex tasks on the system. So not only is it going to generate code to help me run this calculation, it's going to do it through the AIDA workflow manager so we can scale it out. We can make the code resilient to, say, preempted jobs and spot price nodes, and we can run the calculation with a minimal amount of difficulty on our part. This is a Copilot. It is a large language model, which means it gives you code as a starting point. Sometimes you need to work back and forth with the Copilot to resolve issues and customize the calculation. In this case, we'll show you the results, what this does, and it submits the job to the Slurm scheduler. It produces the results of the band structure, and then at the end, it actually shows you what happened in the calculation. This is the provenance graph from the AIDA workflow, and it shows you the steps that were taken, and also actually just gives you a hint into why workflow tools are so powerful. It shows you the complexity that was managed by the workflow tool. So that's one of the ways we're addressing productivity challenges in computational chemistry and material science. And the goal here is to make these tools easier to use. But in order to use the tools, you have to have an environment in which to run them. And that's the second way we're addressing the productivity challenge. Azure Quantum Elements, as you saw from the demo, is designed to provide a very straightforward interface to the types of high-performance computational resources that you need to run these types of calculations. That means you have a variety of CPU and GPU nodes available in Azure HPC. You have high-speed networking, things like InfiniBand, low latency networking that's very important for molecular dynamics and other types of calculations, high-speed storage, and on top of that all, you have optimized workflows. And these workflows use the different, the back end of the system, SPAC, package managers, Conda environments, to make sure that when you spin up different types of virtual machines, you're always using the binaries that have been optimized for those machines. So that's a tremendous amount of complexity that usually a system administrator, or unfortunately too often a scientist, has to tackle before they can actually start focusing on science. And we have a great quote from one of our early customers, Johnson Matthey, where they commented that by switching to this platform, they were able to reduce some of their startup times from 6 months to weeks, and actually be able to also get their scientists back focused on science rather than struggling with the system. This is a sample of some of the tools here on the right-hand side that we've deployed on the platform. It's not an exhaustive list, but it gives you a flavor for some of the organizations and tools we're working with and where we're spending a lot of time making sure that those codes perform optimally on this system. So before we move to the other challenges, let's break and do another poll here. Over to you, Natalie.
Okay, excellent. We'll get that poll shared on the screen. And whilst we're waiting, I'll just remind people that if you've joined us more recently, you can send in your questions to us in the questions box. I will be putting those questions to Nathan at the end of the webinar. So please, have a listen and have a think if you've got anything you want answered. So this poll, we're asking you, which kind of scenario are you most interested in solving? So you've got 4 options there. There is a 5th option. If none of those apply, then please let us know in the chat if there's something else that you're looking to solve, what kind of scenarios, but we'll give you a couple minutes just to put in your responses to that poll. Just seeing if anything's coming in on the chat. Got something for later. Great, so we're getting a lot of people saying materials discovery and molecular screening. So they're the 2 most popular at the moment.
Excellent.
And we do have some others. So please, if you've ticked other, do let us know. And this is our last poll. So if you're enjoying the polls, I apologize, but this is the last one. I know they're fun, but we'll be back to the presentation soon. Okay, so I think I think that's probably about enough time. I'll give you a couple more moments to tick a box if you haven't done so. And let's share those results so Nathan can see what the audience have put. So there we go. Materials discovery is right up there. But yeah, there's a bit of everything in there. So that's probably not a surprise to you.
No, that's great.
Okay, I'll hand back to your presentation.
Okay, thank you. So actually, those results are a wonderful segue to the next session. So we're or the next section of the presentation. So we're gonna go through the 3 technical challenges that I mentioned up front, the 3 things limiting some of the promise of computational chemistry in the past. Those are scale, speed, and accuracy. And we're gonna start with scale. Now, when you think about scale, you think about maybe running very large, tightly coupled molecular simulations. That's an important part of computational chemistry, especially when people are looking at large biomolecular systems or trying to understand, large material cases. But scale is also key to the 2 top answers from that poll. When we screen molecules, we're always thinking about, is my library big enough? Did I look at enough materials combinations? And that's really, if you think about discovery as a funnel, that's a matter of populating the top of that funnel. And scale is essential. Scale really determines how many candidates you can look at, how many combinations you can explore. And so that's why we lead with that example here in Azure Quantum Elements. We scale with high performance computing automation. So Azure Quantum Elements, as I mentioned earlier, is built on Azure HPC. Azure HPC is an extremely powerful computational environment that has core capabilities like the fast, secure networking, including top-of-the-line GPUs and CPUs that you need for high-end simulation. It has high-performance storage, but most importantly, again, on top of all of this are the workflow tools. And those tools are essential for orchestrating the types of scaling problems you encounter. If you need to look at several million, tens of millions of candidates in a molecular or materials discovery enterprise, you're probably not going to be able to do that with a shell script. You need the power of workflow tools in order to manage the complexity of all those different calculations, but also running all those different calculations often on a variety of different hardware platforms so you can get the best performance for your dollar in the calculations and screening process. So screening libraries is a great example. We'll touch on that again a little bit later in the presentation. But I want to talk about a slightly different type of scaling, something we're excited to talk about. It's a product that we've developed with ETH Zurich, Pacific Northwest National Lab, and researchers here at Microsoft. And the focus was developing tools to scale out the exploration of reaction steps. Now, understanding the steps of a reaction are essential for customizing either the catalysts involved in the reaction or the conditions of the reaction to optimize for a particular type of product or to reduce a certain type of say, contaminant or side product. This is an example using this reaction exploration tool to understand one of the most popular reactions in the polymer industry, that's urethane production. And the reason this tool was so important is when you start to look at the underlying possible steps in what is otherwise a pretty simple reaction. We have a catalyst here. It's catalyzing the interaction of methanol with methyl isocyanate to form urethane. But when you dig down into the details of that, there are 1.5 million potential reaction steps that you have to consider in that reaction. We use this tool, this reaction network tool, to scale those out across Azure and then use a variety of different computational techniques tuned for a variety of different virtual machines so we can look at each of those steps in reaction network exploration as efficiently, both from a cost-effective and time savings standpoint as possible. So we go through and screen these steps with semi-empirical approaches. Then we go through and refine the steps to look at a core set of reactions with density functional theory. And then we go through and use high-level electronic structure theory to understand the energetics, in particular the reaction barriers associated with each step. So the next demo here will show you how that works on the platform. So again, we start with the web front-end interface to Azure Quantum Elements. We click through this reaction network tool built on Chematon, but expanded out with additional functionality and using AIDA workflows. This is called AutoRxN. We click into the AutoRxN tool, and our first interface, as before, is a Jupyter notebook. This Jupyter Notebook is where you can configure some of the parameters of the run. You can have it focus on certain types of reactions or prevent other types of reactions you're not interested in. And then it also just gives you a very simple way to look at the starting material. So in this case, we're going to look at one of the most classic sort of organic reaction mechanisms that you see in undergraduate and graduate textbooks. That's the reaction of fluoride with ethyl iodide. Okay, so we launch that calculation, and then we go and actually spin up another interactive session in Azure Quantum Elements to start monitoring the results. And this is the Heron package in the Sign library. Heron is a very powerful tool for exploring reaction networks. And each of these, they have a sort of high-level visualization over here on the left that shows you the steps of the reaction network. And then you can click through, either looking at the arrows, which represent different barriers, reactions with barriers, or you can look at the nodes, which represent products and reactants, to learn more about the reaction network itself. We can start with a high-level view of the network and click into one of the reactions here. And this shows the reaction of fluoride and iodide in the system, again, showing a simple variation of elimination in this reactive system. Now, as you saw that, as we clicked in, we not only got to scroll through the reaction process to see the molecular steps that were involved, it gives us some intuition about what's happening in the chemistry of the system, but we're also able to monitor those steps as a function of the energetics below in the reaction path. And as you remember from basic chemistry, that barrier is what determines the speed of the reaction. And so this is designed to provide a simple interface that you can go through and look at the variety of steps in the reaction. This was a simple reaction, unlike the urethane case, which had 1.5 million candidate steps. Here we only have a few, and we provide different interfaces for more complex reactions so that you can filter by barrier height, and you can start to really focus in on the most interesting, highest flux reactions in the network. So that's an example of scaling, because again, what happened on the back end was a workflow orchestrated campaign of many different jobs to identify the reaction steps, to refine the reaction steps, and then to ultimately understand the energetics with each of those reactions in the process. I want to switch gears now and talk about speed. And again, speed is sort of a central, I think, gripe of most computational chemists and material scientists' life. It's there's never enough time to run the simulations long enough to see all the processes that you want to see. And so we've been focused on addressing some of those speed challenges through artificial intelligence. Now, Microsoft works closely with Microsoft Research, AI for Science Group, that has been really digging deep into what it means to have artificial intelligence models contribute to the scientific process. We've been using many different kinds of AI models to address different speed challenges in computational chemistry and material science. Some of these models are large-scale transformer models that have been trained on a huge amount, hundreds of millions of quantum chemistry data points, and then fine-tuned on experimental data to become particularly good at predicting, say, molecular properties. These could be things like boiling points or solubilities, where we get very, very high accuracy and high generalizability because of the scale of the model, the underlying training on quantum chemistry that gives the model basic understanding of how structure relates to reactivity and energetics, and then follow on fine-tuning through more specific data sets, usually experimental data sets, that make it good at predicting properties like solubility or boiling point, etc. The second type of model we focused on are somewhat smaller but still very generalizable graph neural network models. And these models have two capabilities. They can still be used for upfront screening based on properties. So in this case, we're looking at a materials discovery application, so like one of the top picks from the poll. And we're using these models to do property prediction on candidate materials. But instead of running traditional density functional workflows for those initial property prediction steps, we're actually replacing some of those density functional calculations with inference calls to the machine learning model. This gives us a massive acceleration. We can do those calls much, much more quickly than we could running the density functional calculation to predict that property. We take that set of calls, We filter down an initial candidate set, and then we go and run simulations. But again, instead of running ab initio molecular dynamics simulations, we go through and actually run simulations where we're using a machine learned force field. Now, machine learned force field is again based on this graph neural network structure, and it gives us an additional acceleration. So that first part of our discovery funnel, that initial winnowing down, allows us to look at many, many more candidates. We can study in about a week what would take, the traditional methods would be able to look at maybe 1,000 candidates. We can use this approach, and in a week, we can look at 30 million candidates instead. And that's essential because as you know, with materials discovery, what goes in determines what comes out. And if you're not able to look at very many starting structures, then you really could be missing some of the most promising candidates. Now, we don't rely only on artificial intelligence for these approaches. We use artificial intelligence to broaden the funnel. So instead of looking at 1,000 candidates in a week, we're able to look at 30 million candidates in a week. And we use artificial intelligence to help winnow that huge search space down to the most promising candidates. Let's say in this example, it's 800. We then take those 800 candidates and we run the traditional density functional approaches afterwards. This is important for giving confidence to the scientists who have to go off and make these at the end. But it's also important because those density functional theory calculations, the more traditional physics-based simulation, gives you insight into the system. So it gives you that explainability piece. Again, explainability is important for building confidence in the results, but it's also important for generating that insight needed to optimize these candidates down the road. So we believe that AI and HPC are sort of an inseparable combination. AI helps you broaden the funnel because it's so fast. It accelerates those steps. You can look at many, many more candidates, but it goes hand in hand with the traditional physics-based calculations where you use high-performance computing to run simulations and really get that detailed insight into the system. And the result here was that we were able to essentially compress 20 years of calculation into about a week. And that really transforms the way you think about finding new materials and executing discovery processes in this space. And it was only possible because of artificial intelligence. So one of the steps I mentioned on the previous slide was using artificial intelligence and machine learned force fields in simulations. Now, those of you who are familiar with molecular simulation that know that anytime you replace a quantum mechanical process with some classical representation, you're making compromises. In traditional molecular mechanics approaches, those compromises are the use of, say, springs and torsion potentials to try to describe the system using an empirical representation. Artificial intelligence is data-driven, so in this case, you're training a model based on examples that you've presented it with, and usually those are the most common states of a system. The problem is in chemistry and material science, it's often not the common states that we're interested in. We're interested in those rare states, those reaction processes that we're trying to catalyze. We're trying to find materials to catalyze. That means it may be the rarest events that aren't in the training set that have the biggest impacts on the quality of the simulation. So like academic groups, including the Kaczynski group at Harvard, we've started to explore techniques for using an active learning workflow in this space. You can think of active learning as running a simulation with a machine learning force field that's aware of its accuracy, or it's at least aware of the uncertainty associated with its predictions. You run the simulation, and you continue to produce forces or energies depending on the type of simulation. But those forces are equipped with uncertainty estimates so that you can start to monitor when the force field is confident in what it's producing versus when the force field is start to become uncertain about some of those results. As the uncertainty reaches a threshold, you can pause, and the active learning workflow allows you to retrain the simulation, in this case on density functional calculations that can give new force information to fine-tune the force field. These two work hand in hand, and they give you the ability to pre-train these force fields. For example, you can run the simulation with the active learning workflow, explore some of the unusual conformational states, and tune this up front, or you can be doing it on the fly during the simulation. The net result is that you gain the benefit of the machine learned force field in speed, and that benefit is really remarkable. it can give you about a 500,000 times speed up over traditional ab initio molecular dynamics. But because of the active learning framework, you can balance that against accuracy requirements, and you can maintain accuracy in the simulation for forces and energies that are comparable to the original density functional calculations. So what that means is you get a 500,000 times speed up with very little compromise in accuracy. And perhaps more importantly, this forms a dial that you can tune over the course of the simulation. So you can be more conservative or less conservative depending on the requirements of your simulation. So that's a second aspect to speed. It's a really powerful tool available in Azure Quantum Elements. I want to wrap up the presentation by talking about accuracy. And as I mentioned at the start, accuracy is the third technical challenge that we're working to address with Azure Quantum Elements, and it is the primary target of quantum computing. When you run classical simulations of quantum mechanical processes, you have to make approximations. And this curve shows why we make those approximations. The complexity and the cost of running classical computing solutions to quantum mechanical problems increases exponentially with the number of electrons that we're studying. And at some point, that growth becomes simply, results in time or memory constraints that are simply too large for any classical computer on the planet. Right now, the way we address that growth is by making approximations. We reduce our system down to a density functional problem, and we stipulate a certain exchange correlation functional. We use couple to cluster approaches, but we truncate at singles and doubles and those types of interactions. We make approximations, and in many cases, those approximations can affect our accuracy. So the promise of quantum computing is to allow us to eliminate those approximations and have essentially ground truth for our quantum mechanical description of the system. Now, I want to talk a little bit about how we think about quantum computing in this space. We're focused on chemistry and material science because although quantum computers will be very fast, they will also be much, much slower than their classical counterparts. That's partly because you need a classical computer to drive a quantum computer. So when we think about the benefits of quantum computing, we don't think about the asymptotic scaling. We don't think about what happens when the problem size goes to infinity, because in general, no one wants to wait an infinite period of time for the answer to their problem. Instead, we look at the benefits of classical and quantum computing with a crossover time of about a few weeks, which is probably how long someone's willing to wait for that ground truth answer to quantum computing. And so that's why we're so focused on quantum chemistry and material science problems. When you focus down the problem time to the span of weeks, not years or centuries, you narrow down the space of applications that'll benefit from quantum computing. And that's really where chemistry and material science stand out. So that's the promise of quantum computing. How do we actually get there? What we've built into the platform is ways to study these systems, chemical systems, to understand which parts are in need of approximation, or better yet, in need of computing innovation to remove the approximation and improve accuracy. But those can be very challenging. Understanding which parts of a molecule are doing interesting things is the domain of so-called active space methods. And what we've built into the platform is a way using tools like AutoCAS to go through and, when presented with a molecular system, identify the set of electrons that are exhibiting entangled or correlated behavior. Now, not all electrons in every molecule have this property. And that's very exciting because it means when I think about the complexity of an electronic structure calculation, especially without making approximations, I don't always need to consider every electron in the system. I just need to consider electrons in those active space problems, those electrons that have that entangled or correlated behavior. So we built in tools in the system that will allow you to automatically identify the active space, to automatically identify that set of entangled electrons. And then it presents the user with a decision. If the active space is of reasonable size, and this is usually 20 or fewer orbitals, we have tools available on the system that will allow you to go in, start a very large memory Azure HPC node, say 4 terabytes of memory, and run what's called a full configuration interaction. And that is a solution to the accuracy problem today. Without a quantum computer, you can go in and you can run one of these calculations for relatively small systems of less than 20 orbitals and remove the need for approximation and their impact on accuracy. That's one choice. If the system is larger, if it's more than 20 orbitals in the active space, we provide tools that allow you to go and either simulate or estimate the properties of a quantum computer that would be needed to model that system. So we have a resource estimator built into Azure Quantum Elements. So we've given the active space of the system, it will build out the quantum circuit, and then it'll go through and run estimates of the resources needed to execute that circuit. And the answers are very interesting. For systems of 40 or more orbitals in the active space, the answers that come back are that you need 1 million well-behaved physical qubits. So these are physical qubits with error rates in, say, 10 to the minus 6 regime. So they're already better behaved qubits than exist today. And we need about 1 million of them because they need to work together in sets of maybe 1,000 to form logical qubits to execute this problem. So this is exciting that we can go and understand what we need from quantum computing resources. It also motivates the need for solutions today because most analysts' estimates put 1 million well-behaved physical qubit machine at about 5 to 10 years off. Our goal with Azure Quantum Elements is to make sure that we're an on-ramp to that future quantum supercomputer, but that we're also providing tools that can be used today to address accuracy challenges along with the speed and scale challenges that I mentioned previously. Finally, I want to talk about what you can do today with quantum computing on the platform. Now, there aren't any quantum computers on the planet that right now that will outperform a classical computer in this problem space. But there are these noisy intermediate scale quantum computers offered through Azure Quantum that you can work with to study very small problems. So if you have a system of 2 atoms, for example, lithium hydride, and you're curious about how quantum algorithms will perform on this system, you can compile this down into a circuit and you can run on the NISQ, noisy intermediate scale quantum machines available through Azure Quantum. This doesn't offer a speed benefit over traditional classical computing, but it does help you start to think about what quantum computing will do for you in the future. It helps you get familiar with how the algorithms work in this space, and it helps you experiment on systems that might be of interest to you. So those are the 3 technical challenges: speed, scale, and accuracy. And with accuracy, we're focused not only on solving accuracy problems today, but also building an on-ramp to those future quantum supercomputers. And this is all based on the foundation of Azure Quantum Elements as a computational cluster, a platform that makes it very easy for you to get up and running using computational chemistry codes, using Copilot to reduce some of the barriers to those codes, and having the infrastructure necessary to run those codes at your disposal, pre-configured and deployed as part of the platform. We're excited about the benefits and the value of Azure Quantum Elements, but we're not the only one. About a year ago, we started working on this system. We also started quietly discussing with leaders in chemistry, material science, and life sciences about what they need to solve their problems. What would it mean to them to accelerate scientific discovery in chemistry and material science? And what do they need to make that happen? And so these are some of the customers that we've been talking with and that are working on Azure Quantum Elements today. We are in a private preview stage, and we really value the input of these and other partners in helping us understand some of the biggest challenges facing chemistry and material science, so we can be developing the capabilities on Azure Quantum Elements to address those challenges. This is a quote from one of our earliest customers, BASF, and it's an exciting quote for us because BASF is well known for their work in high performance computing in computational chemistry and material science. Their new Curiosity 3 machine is a truly amazing instrument. But despite all of those computational resources that they have on premises, they saw the value in reaching out and starting to work with new computing platforms and new paradigms to get that speed and scale and accuracy boost that Azure Quantum Elements offers. I want to wrap up with a video here. This is from Misbah Sarwar. She's a research lead in physical and chemical modeling at Johnson Matthey. She's also an RSC member and I think pretty active in the society. So I think it's a great way to wrap up the talk.
Thanks, Nathan, for inviting me to speak with you today. And hello, everyone. My name is Misbah Sarwar, and I am the research lead for the Physical and Chemical Modelling Group at Johnson Matthey. And my team work on modelling across length and timescales, from atomistic to engineering scales. I'm an atomistic modeller and have a background in DFT and molecular dynamics simulations. And I apply these techniques to study a range of catalytic reactions, ranging from NOx reduction to clean up emissions from the internal combustion engine to looking at new alloys for PEM fuel cells. Johnson Matthey is a global leader in sustainable technologies, providing scientific expertise to help enable cleaner air, improve health, and make more efficient use of our natural resources. And today, we're particularly interested in accelerating the transition to net zero, focusing on transport, energy, and chemicals production. The Physical and Chemical Modelling team is part of our core capabilities group, whose function it is to provide the underpinning science and engineering, which can be applied across Johnson Matthey businesses. In the modelling group, we are spearheading digital simulations and use predictive modelling tools that can help us drive research into new sustainable technologies. Over the past few years, we've worked with Microsoft to move our digital simulations to Azure to provide each of our scientists with cloud supercomputing facilities. The migration alone has provided a modernized environment for speeding up and optimizing our computational workflows and simulation parameters. Using tools like AIDA and various DFT codes like Quantum Espresso, we've seen a workflow runtime acceleration of up to 50%. For example, we might get asked to make a prediction about what material might be active or for a particular reaction, and that might mean that we have to screen through hundreds of different combinations of materials and dopants. And to do that, we need access to a lot of compute resource, and the Microsoft platform has enabled us to do that in a more timely and efficient manner than we were able to do previously. And so now we don't have to wait very long to provide insight to our experimental colleagues. So not only has Azure Quantum Elements helped modernize our environment, but it's also allowed us to expand our digital research into new areas. So for example, we can simulate spectra to aid our experimental characterization scientists, and we can simulate more complex or more realistic models, looking at things like nanocluster and adsorbate interactions, which can help us identify better alloys for fuel cells that could use more sustainable sources like hydrogen. Traditionally, this type of research has been a highly complex task with significant scope for optimization. But with Microsoft's researchers and the Azure platform, we've been able to pioneer new predictive modeling tools to accelerate these simulations. Azure Quantum Elements provides us with a system where we can significantly grow our research team, arm them with state-of-the-art computational tools, and continue to drive new insights. As these disruptive computational tools advance further, so will our impact to pioneer better solutions for a sustainable world, and that is extremely exciting. Thank you very much.
Well, thank you to Misbah for taking the time to share that message, and also thank you to Johnson Matthey for being such a great partner. It's essential to have leaders in the industry like Johnson Matthey help shape the platform, and it's really contributed a lot, I think, to the capabilities that it can offer the chemistry and material science community. So I'll just wrap up with a final slide here. Again, Azure Quantum Elements was designed to address that critical need, that existential need of accelerating innovation in chemistry and material science. It's a platform that first and foremost improves productivity in this space, but also addresses technical challenges associated with scale, speed, and accuracy, three things that have limited computational and material science in the past, but are now addressed through this platform. So we have a variety of links here where you can sign up for the private preview or learn more about its capabilities. And I'd like to just conclude by thanking RSC for the opportunity to present this, and to all of you for your time today listening to the seminar. I'm happy to answer any questions. Thank you.
Thank you so much, Nathan. That was, well, actually somebody in the chat have said that was awesome. So that's great feedback for you. I don't think you can do any better than that. So For the audience, we've got a couple of those links in the chat, so you can click directly on those to check out any of those. But we do have time for some Q&A now. So if you've got questions that you want to ask Nathan or the team, we've got some of the team in the background who, if you've asked a question, you may have noticed you've had a response sent back to you. They're working in the background to try and get through some of the questions as well. Again, if we don't get time to answer your question, or you just have another question that comes to you at the end of the webinar, then you do have the contacts there for how to contact Microsoft to follow up after this. And finally, if you've missed anything, or if you need to go back and check anything that Nathan has said, a recording of the webinar will be sent out to everyone who registered, and you can register after the event, so you can tell your friends and colleagues if they want to catch up with this. So you can go back and watch in your own leisure. So let's see if we can get through some questions. Yeah, we've got more great comments, great presentation. People seem very excited about this software, so this is great. One of the first questions that's coming in is a really useful one. Now, they saw the demonstration of the AI capabilities with Copilot, and this person's asking if that's integrated into Azure Quantum Elements, and if so, how? Okay, now that's a great question. So I showed two interfaces to the Copilot. The first you can access right now. It's a demonstration about Copilot for information retrieval in chemistry and material science. And you can go and run that through the web at quantum.microsoft.com. So that's available to everyone today, intended as a demonstration for, sort of a way to explore Copilot in this space. The second one, the demonstration I showed for Copilot integrated into the platform itself through Jupyter Notebook, is something that we're developing. It exists now, and we'll be rolling it out to our early adopters over the coming months. So it's an exciting way to interact with the platform. We're still fine-tuning some of its capabilities. You can see the demonstration today, and you can use it if you sign up for the private preview in the coming months. That brings me on to the second question. Yeah, is it available already, and how can people try it? What's the best way to get involved with this now? Yeah, for the information retrieval one, quantum.microsoft.com gives you an opportunity to do basic question answering, get answers grounded in the scientific literature in chemistry and material science. To use the one on Azure Quantum Elements, you'll have to sign up for the private preview, and that'll give you access to that in the future. Okay, fantastic. Okay, lots of questions still coming in. Brilliant. Let's keep them coming. Right, another question that we've got coming in is about the Reaction Network Explorer. And somebody is asking, how complex of a reaction can they study? That's a great question. Right. So Azure HPC is huge. We have many computational resources there, so we can look at very large reaction networks. But for most customer problems, even just trying to get your hands around the volume of data that the reaction network explores, we think about systems with about 100 active atoms in the system. So that's 100 atoms that have been configured to allow reaction within the system. You can look at somewhat larger molecular systems. You can turn off reactions between certain atom types, but that core set should be about 100 atoms. And that opens the door to lots of problems in homogeneous catalysis, lots of problems for understanding, say, degradation of molecules and other unimolecular, bimolecular types of processes. Okay, brilliant. So let's have a little look. So, it's fairly new what we're talking about, and, you're getting lots of interest already. And I like that, we've shown that Johnson Matthey example, and you've been working with different companies. But one of the questions is actually related to how, what are the most popular uses that customers, what cases are they using most popularly with this software? That's a great question. Not surprisingly, it maps to the poll that we showed earlier. So we see a lot of people exploring problems in catalysis. So either using traditional density functional approaches and taking advantage of the scale possible on Azure Quantum Elements, or starting to experiment with some of the machine learning force fields and active learning approaches to accelerate calculations, especially in heterogeneous catalysis types of problems. Additionally, one of the big advantages of a platform that can scale like Elements and the workflow tools that allow it to scale is discovery. So whether it's small molecule discovery or a materials discovery, again, you can take advantage of scaling out those calculations for traditional physics-based approaches, but also accelerating some of those with
with machine learning and artificial intelligence. And there's a much longer tail to the distribution of what people are doing on the platform. I don't want to limit it to just those, but those are some common examples that we see right now in terms of use of elements.
Okay, thank you. So yeah, let's on to my next question I've got scheduled here. Still lots coming in, it's brilliant. So someone's asking, Vivek is asking, is it possible to add their own software packages, for example, Gaussian? And in that case, they're wondering how the licensing would be handled, if that's something you can answer.
Yep, we provide a core set of open source and some Microsoft developed packages on the platform as a starting point. But of course, we realize that every customer has different needs. They're going to bring their own codes or they're going to bring third-party commercial codes to the platform. We make that possible. It's a bring your own license type of process. So we don't want to get in the way of the relationship between other commercial software developers and the customers. So once they've worked with the vendor like Gaussian to get a license that permits use on Azure, then we work with the customer to make sure that that code is running as efficiently as possible, and we're helping them pick the right VMs to get the best performance out of the code. So we're very open to third-party codes, and we work closely with the customers to make sure they have everything they need that isn't already on the platform when it's deployed.
Okay, that's good to know. Somebody else is asking that they've seen the Quantum website and that there's a Copilot page, and they're wondering if that's the same as the one you mentioned before.
Yes, if you go to quantum.microsoft.com and you select at the top, there'll be a drop-down menu. You actually see a couple different Copilot experiences, and this represents the different ways that Microsoft's innovating in using Copilots to help solve and accelerate discovery for complicated science problems. So one of these is actually quantum computing. And if you click through to that one, you can start to see how Copilot can help you generate code to interact with quantum computers. But the other one is the chemistry and material science Copilot that I mentioned earlier in the talk that has that information retrieval interface.
Okay, that's good to know, thank you. And another question about Copilot. They're wondering what's inside Copilot, which sources is it currently connected to?
Right, so Copilot's based on Azure OpenAI services, so it's using GPT-type models to drive the inference. Then we use something called grounding data, and we actually intended this originally as a demonstration because the way grounding data works is the LLM uses it as a source of information, but the grounding data stays inside that subscription. So if this had happened to be company proprietary information, it never leaves the subscription. It's not used to fine-tune anything. In the case of the example at quantum.microsoft.com, that grounding data are things like open source software manuals, tutorials, examples, as well as several 100,000 examples from the scientific literature of articles that have been licensed in a commercial friendly way so that we could use it for this system. So when you ask a question of that Copilot interface, you should get back an answer that includes several footnotes, kind of like you see with Bing AI or Bing Chat, that tells you the sources that information came from, which in most cases, just because of the number of articles on the platform, it'll be something from the open source scientific literature.
Okay, now we are running short on time, but actually this is quite a good question to end on, I think, because someone's asking about how their data will be kept safe if they're using the AI tools, which I think is a really, really important question that we cover. So yeah, have you got some information on that?
No, that's a great way to wrap up. First and foremost, Microsoft respects customer privacy. It's very, very focused on privacy, particularly given the advent of AI tools. And we have several articles in the Microsoft blogs talking about our privacy promise and how customer data is never used to go back and train a model that's used for anyone other than that customer. And that's the case here, right? So all of the data that's used stays with the customer, it stays within the customer's Azure subscription, and no one else has access to it. And that again, that's just part of the core Microsoft commitment to privacy and AI.
Okay, thank you. That's good to clear up. Okay, well, I'm afraid that is all we have time for today. These hours always go so quickly and there's so much information to take in, but thank you so much to Nathan for joining us from Microsoft today to speak about Azure Quantum Elements. There's been a lot to take in, but as I said, if you need to go back and watch the recording, it will be available in a couple of days and emailed out to you. And thank you to our audience for getting involved in this conversation today. We've had some fantastic questions in. There's been a lot of engagement in our polls, so thank you for joining in. Again, if you have further questions, or if we didn't have time to put your question to Nathan, then please look in the chat for how you can contact Microsoft and the team, and they'll be able to get back to you. So if you've enjoyed this webinar, please do check out chemistryworld.com/webinars for our future events. And while you're there, you might want to register for a Chemistry World account, where you can sign up to our very popular reaction newsletter that includes a weekly digest of big stories from across the world of chemistry. But as I said, that's all we have time for today. Thank you so much for joining us. I'm Natalie Starkey, Chemistry World Science Media Producer, and I look forward to seeing you again in a future Chemistry World webinar.